My name is Chris Johnston. I'm a researcher here at AFBI, and I can see a few of you might be looking to see what's going on with those experiments, but we can carry that later on. Chris Johnston and my colleague John McIlroy. We've got about 8 or 10 minutes here, and we're going to split it 50-50 between John and myself. I don't know how much conversation you've had today or previously about nutrient excesses, nutrient surplus, anything like that. It may be familiar. I think Francis might have mentioned at the end there about our excess phosphorus within our agricultural system. And that's really what I want to talk to you about. We have a phosphorus a phosphorus surplus in Northern Ireland currently of about 11 kilograms per hectare per year. Is about what we are. That needs to be a good bit lower. We've also got an excess of nutrient in the country of about 6,000 tons of phosphorus, which we want to aim to try to remove. And that's really the whole basis of what I want to just run through you. Piece of work we've been doing with the Department of Agriculture and Environment is to kind of investigate the feasibility with a number of organisations and associations of companies, the feasibility of actually trying to remove that phosphorus from the farm base. And I want to run through that with you. So we've been aiming essentially at high nutrient farms with excess slurry, farms with maybe high phosphorus indexes in their soils, farms that could really do with having to remove that phosphorus into somewhere else. So we've been aiming at those kind of farms with the potential of either static screw presses or mobile screw presses, something to actually separate that. I don't know if any of you run screw presses or are familiar with them. We do have one running on the other side of the farm if you're interested in one of the focus groups to go up and have a look at. But when we do run a screw press, what we're doing is we're essentially putting that slurry through the screw press, and we're sort of putting most of that phosphorus, partitioning a good bit of that phosphorus, between 20 and 40% of that phosphorus, into the solid portion. Our own experimental work shows us we're getting about 30%. There's ways to increase that as well. But if you can push that phosphorus into the solid material, then you've got a material that's actually exportable from the farm. And that's the next step of what we've been doing with the department, is separating that, and we would tend to move that towards AD plants, call them biorefineries, whatever, but anaerobic digesters, because that material now is a feedstock. That's a feedstock for biomethane potential, but not only for biomethane, also for nutrient valorization at the end. Why are we so interested in the biomethane? Well, our fossil gas system is what we rely on at the minute. Remember, a couple of years ago, we ran into terrible trouble with gas prices going very high. If we have some reliance on our own gas, and there's the academic studies would show that we have a good opportunity of displacing actually quite a lot, a significant amount of our gas with biogas, and that's where we really will come in here. But look, mobile screw presses is something I think we're going to see an awful lot more of. Static screw presses, not for everyone. Anaerobic digestion, and then ultimately the digester that comes out the back end, that'll have a much more concentrated phosphorus load in it. That's where we want to now introduce the valorization aspect, which means adding value. So we're talking about different carbon products. You hear a lot about biochar, different fertilizer products, phosphorus fertilizers, blended fertilizers, organomineral fertilizers. You know, we have a need for these materials, but not in Northern Ireland. That's where we need to kind of reduce that excess that we have and start to protect water quality to a better degree. But I'll focus on that a wee bit more. So by going through this whole process and funneling that phosphorus into the solid portion, removing it through an AD plant, pulling out the biomethane, getting the nutrient right through to the end, we have an opportunity of not only producing the biomethane and reducing the reliance on imported fossil fuels, but we have an opportunity of valorizing these compounds as well. The nitrogen, the phosphorus, even the carbon dioxide, there's ways to valorize that. And we do need to create that value in order to make that export possible, because that's really what we want to aim at. Lower carbon footprint for agriculture. The whole point, again, just to re-emphasize it, because it is the whole point of why we're even talking about this, is to reduce that farm P balance, to bring the phosphorus balance down in the farm, to reduce that nutrient pressure on the agricultural land base, and then subsequently then start protecting water quality to a greater degree. The Climate Change Act, we're all aware of the Climate Change Act. It's legally binding. Every sector has to reduce its greenhouse gases right down to a net zero. Agriculture is no different. It's harder for us, though. It really is harder. But these are all ways to start to address this. And of course, everything I've spoken about here are opportunities for new jobs, green jobs, call them green jobs, because we don't really have these industries at the moment, but we have the potential to have them. So these are green jobs, and we hear a lot about green jobs from government, I think. Key messages. Runoff of phosphorus from our agricultural land base does cause over 60% of our phosphorus pollution on our waterways. It's indisputable. Removal of that phosphorus and reducing that excess can really start to improve water quality by reducing that nutrient pressure. That's what we're aiming at through this whole process. I'm touching this one in a second. We need to evaluate the cost models here, and this is what we're doing in conjunction with the Department of Agriculture at the moment. This whole thing has to be affordable. It has to kind of make sense. If it starts to make sense economically, then we can start to develop the environmental sustainability of the whole thing as well. So that's a big part of the workload that we have to do. And of course, we need acceptance. It's very possible that a lot of you haven't really heard of this kind of a plan before, and that's why we're trying to investigate it. But we need to get sort of acceptance from the agriculture community, from the environmental community, the NGOs, anybody, any stakeholder essentially in sort of agriculture and our environment. We need that acceptance because we're talking new technologies, new practices, new products, kind of a different direction, if you like, to improve the sustainability. No point in doing any of this, of course, if we're going to pollution swap or if we're going to risk our biosecurity. These are all vitally important. We cannot take our eye off that ball, of course. No point pollution swapping, controlling phosphates if we're going to then suddenly start to emit enormous amounts of biomethane, really, potent greenhouse gas, or indeed ammonia and cause more pollution in our air. But look, while I'm finishing on ammonia, I'll pass over to John, who knows an awful lot more about ammonia than me. So, John, I'll fire on to you.
Yep, thank you. So as I was just saying, I noted a couple of you were looking towards the experiment that we have over here behind us. Just to let you know what that is, this is a trial. It's funded by the Department of Agriculture, Food and the Marine in the Republic of Ireland, and also DAERA here in the north. And what we're looking at here are emissions from fertiliser application and also from organic manure. So we've got some NPK fertilisers here, those stainless steel chambers that you see there. That's for the measurement of nitrous oxide emissions. So we're measuring, it's a greenhouse gas, we're measuring nitrous oxide emissions from inorganic fertilisers here, so NPK fertilisers with different levels of nitrogen in them. Over here further to the right, there are some more static chambers there because we're also measuring nitrous oxide emissions, but we're also measuring ammonia emissions over here, and those tunnels that you can see, those are called ammonia wind tunnels, and we're effectively measuring the ammonia emission generated by effectively the footprint of that tunnel within the plot area here. Further over, you've got more static chambers, and what we're measuring over there are actually nitrous oxide emissions from organic manures. So things like digestate, separated liquid fractions, acidified liquid fractions. So linking into the research that Chris has alluded to. But back onto the theme of the talk here and of the stop. Chris has been talking about kind of the biocircular economy and how at a regional level we need to have much more biocircularity. I'm going to bring that slightly down to farm scale again and just talk about the nutrient circularity on farms, and equally, we may need to export excess nutrients from our farm, but it's also about maximising the nutrients that we have on our farm and trying to reduce the emissions of those nutrients to the air and to water. So one of the key farm nutrients, of course, is nitrogen, and probably the major loss pathway for nitrogen, particularly within livestock systems and grassland systems such as ours, is actually as ammonia gas. So we get ammonia being emitted from our livestock manures throughout their management, so from the house, from the store, from the land spreading, and also from fertiliser application, particularly if we're spreading urea fertiliser. So ammonia gas, as we're losing a form of nitrogen, agronomically it's a problem for a farmer. It's going to cost you money to have to import in an inorganic form the nitrogen that you've potentially lost from your organic manures and from your fertilisers. But also there's an environmental repercussion because the emission of ammonia actually has a negative impact on protected sites. So for the past 4 or 5 years, DAERA have actually funded quite a large programme of work in the ammonia emissions for research here at AFBI. And today I'm just going to touch on some of the findings from that research, particularly focused on the beef sector. So what we did was we used the UK ammonia inventory model to model a series of scenarios. We did this for the beef sector, for the dairy sector, for pigs and for poultry also. But I'm just going to present some of the scenarios that we looked at and how, by applying some ammonia mitigation strategies to what are typical beef enterprises in Northern Ireland, we can achieve significant reductions in ammonia. So the first scenario here is a 24-month steer dairy origin beef system. Within that, we modelled 22 finishers and 22 calves. The grazing period was set at 192 days. I'll mention in a second why that's important. In terms of the housing system and how specifically the manure is managed, well, 66% of the manure from this system is managed as slurry, so it's on a slatted floor with an under-house store, but 33% is managed as farmyard manure, so there's a component of straw bedding in this system, which gives us, farmyard manure also to manage on the farm, and that's stored in a heap. The slurry is spread by inverted splash plate, and the farmyard manure would be spread through broadcast application. There's also a fertiliser application associated with this scenario, so there's a combination in there of both urea and CAN. The second scenario is a less favoured area, hill suckler cow spring calving system. So 18 beef cows and 18 calves. Grazing period here slightly lower, 180 days, reflecting the LFA conditions here, which would reduce the possibilities for grazing. There's no farmyard manure in this system, there's no straw bedding, so it's just a slatted floor slurry system with the slurry stored under the house and then the slurry being spread by splash plate to land, and there's no fertiliser application with that scenario. So what we did was we took 5 ammonia reduction strategies which are proven and we know by how much they can reduce ammonia emissions, and we applied them to those 2 scenarios. So very briefly, the 5 strategies were extended grazing by 2 weeks. So that could be a week at either shoulder of the season, so potentially an extra week in the spring and an extra week in autumn. Now, I know practically it may be difficult with conditions and there are going to be other driving factors here that may make that difficult. But we effectively modelled what the impact of extended grazing by 2 weeks would have on ammonia. We also modelled the use of slap mats, so slap mats which are applied to the, slotted onto the existing slatted system and have a sort of a curvature to them. They allow urine to drain from the flooring surfaces more quickly, which reduces our housing emission. We applied those to the mitigated scenario as well. We also modelled increased house scraping. So if we can increase the scraping of our passageways and areas in the house that have maybe scraping to every 2 hours, which is seen as the optimum frequency to reduce ammonia emissions, again, that can reduce emissions by anywhere up to 20% in the house. Crucially then, because this is one of the big mitigation strategies, we moved away from slurry spreading by splash plate to spreading slurry in this scenario by trail and shoe, but equally it could be another low emission spreading type of equipment, so for example a dribble bar or maybe a shallow injector. And finally then, for the fertiliser, we moved away from straight urea to the use of protected urea, which is urea coated with a urease inhibitor, which decreases the ammonia emission as our final strategy. So when we applied those 5 strategies to those 2 scenarios, we actually found that there was a 34% reduction in ammonia achieved in the 24-month steer, dairy, origin beef system, and a slightly higher 42% reduction for the LFA hill suckler cow system. Now you might ask why the emission reductions are slightly different if we've applied the same strategies. Well, largely in this case, it's due to the management of the farmyard manure in scenario 1. Obviously, farmyard manure isn't going to lend itself to spreading by low emission spreading. It has to be broadcast, which inevitably, unless it's been ploughed in rapidly, you're going to have an emission from that material. And also it has to be stored in a heap, which generally will compost probably more. It's exposed to the atmosphere and to the air more than a slurry tank would be, which is generally more anaerobic and may crust. So you also have a slightly higher emission from the heap, which means the reductions weren't as high for the first scenario. But overall, look, significant reductions are achievable across both, particularly with the alteration of some of our management strategies. So for example, extended grazing, increasing maybe the scraping frequency, but it is going to require some investment on the farm, looking at the flooring systems, potentially slap mats, that might be an option, and particularly, crucially, moving away from splash plate to a low emission spreading method, because of that 34 and 42%, this is going to be a big chunk of that reduction. And finally then, what we did was we decided we wanted to look at some of the new housing systems that have become available and are seeing commercial expansion across Europe, so places like Holland, Germany, Denmark, and model those and look at that in comparison with our sort of typical setups here in Northern Ireland with some of our built-in applications applied. So here we looked at an in-house slurry acidification system that achieved a 73% reduction in ammonia, and we also looked at a negative pressure air scrubbing housing system which achieved a 70% reduction in ammonia. So look, significantly higher than what's achievable through the application of some of these more retrofittable technologies and tweaks on the farm. But again, look, those systems are going to have higher capital costs, so more expensive to build, more expensive to run, and also probably retrofitting these technologies, so retrofitting acidification or retrofitting air scrubbing to an existing housing system is probably not going to achieve the same reduction efficiency as if you build the actual house around the technology itself with the bespoke housing system. So look, that concludes my brief presentation. I'm just going to open it up now to questions across the board for both Chris's talk and for mine.